Hello everyone, I'm Ghasem Sharifi and today I'm gonna present the progress that I made during last year. My thesis title is Design and Validation of Avionics System of Deorbit Device Based on Electrode Dynamic Tether, and my supervisor are Professor Gonzalo Sanchez Ariaja and Professor Andres Marcos. First, have an overview of the content of this presentation. First, I will recap the ATPAC mission, and after that I will present the summary of the progress we made during last year's, and after that I will go through the contribution I did during this project that was on the attitude determination and control subsystem, and also on the mission operation and ground station. Electrodynamic tether is a promising solution for deorbiting a space debris, and the ATPAC is basically according on this technique, and we are working on developing a deorbit device that we want to launch it next year, and basically it includes two different modules that will separate during the mission with a 430-meter line tether. And just in order to, just as the example of the performance of this system, if we have a satellite at 600 kilometers without any deorbiting device, it takes more than 10 years to deorbiting. And if we only deploy tether, this deorbiting time decreased to 3 months is only because of the aerodynamic drag. And if we have a Lorentz force, the electrodynamic tether works. So this time is going to less than 70 days. During the last year, we did a qualification test campaign. So we did prof pressure test, we did the leakage test, we did the burst tank pressure, and we did functional test of the cold gas system. We did partial deployment test, and after that, we did vibration and shock test in order to tackle the shock and vibration that we have during the launch. We did thermal vacuum cycling. We did electromagnetic compatibility test. We characterized the magnetic dipole of the deorbit device. We did HDRM test in order to be ensured that the module will be separated during the mission successfully. We repeat again the vibration test. We did full tether deployment test in order to be ensured that the entire tether will be successfully deployment during the mission. We did also ADCS validation test, and we did also partial tether deployment in the thermal vacuum chamber in order to mimic the most similar to the condition that we will have in a space. And finally, now we are doing telecommunication tests. And over all of these tests, I was responsible for magnetic dipole test, ADCS validation test, and telecommunication test. For the attitude determination test, as you know, is one of the subsystems, very complex, lots of sensor actuators working together in order to provide stability and control pointing, and also in order to determine the attitude of the satellite. We have two modules, and both modules have a separate ADCS system. You can see here the placement of the sensor actuator in a satellite. And also here is the schematic of ADCS architecture, how the sensor working with the microcontroller and sending command to the actuator. And for that, we follow the V-shaped validation process for mission requirement, software designing, analyzing the output of the software. And after that, for validation, we did the software in the loop, processor in the loop, and hardware in the loop test in order to being sure that subsystem work properly. And we did different tests for evaluation of the microcontroller algorithm execution. We did also for evaluation of attitude determination algorithm that was based on the extended Kalman filter. We did also a fault detection and isolation validation test. We also did the performance of the end-to-end ADCS subsystem, and finally also we did the estimation of the residual magnetic characterization. And for all of this, first we should have an experimental setup. We didn't have in university the setup for testing ADCS. You can see here, first we provided 3D degree freedom of air bearing that can provide for us ability to rotate dynamically the deorbiting device. Also for eliminate the gravitational, we did a balancing system. We use a sun simulator in order to mimic the light of the sun. We did also ground station in order to monitor the behavior of the satellite. And also finally, we did the attitude reference in order to making the air to pointing the satellite. And for that, this does some example of the hardware in the loop test that we did. For the sun sensor validation, we are using the photodiode in order to getting the vector of the sun. So we simulate exactly the characterization of the photodiode in a satellite. We did a 1U CubeSat, so we evaluate the vector coming from the photodiode. Also, we did algorithm validation using, by comparison, the result of the attitude with the high accurate reference system. And also we did end-to-end testing using all of the sensor actuator in a satellite, and also implemented algorithm in a microcontroller to being sure that all of this system working together properly. This is also some of the ADCS result. We did this test in different conditions with different initial condition. We did in a sunlight, in eclipse condition, to knowing the system work in all of these conditions. Also, we intentionally didn't apply some failure in different sensor to knowing also, because for our ADCS, for each sensor, we have also the backup sensors, just to knowing that the backup sensor also working properly during the mission. Also, we intentionally apply some failure during the test, and you can see also here some of the results of the test. One of the important things for us is to characterize the magnetic dipole of the satellite. In a satellite, we have lots of wiring, electronic devices, and ferromagnetic elements. So it was very important to knowing the dipole of the satellite, and it's very important because when we are in a mission, because of the interaction with the magnetic field, generated disturbance torque. And specifically for the satellite, using the magnetic torque is important to knowing the amount of this disturbance torque. So we should characterize this, and therefore there are some setup to estimate for us at what it was very costly and was not accessible always for us. So the baseline design was to have a setup in a satellite, in a university. So based on the COTS magnetometer, and we developed a specific software for estimating the position, direction, and also the magnitude of the dipole. And also we was aimed to not using the turntable that need a very large space. So we did a software design, we did the 3D modeling, we also the manufacture with the 3D printing without using any metallic material. We calibrating the sensor, and you can see here the setup that we have now for testing and characterizing the dipole of the satellite with the network of the magnetometer working together to estimating the dipole. And after that, we did some validation setup, and also we putting the satellite there, and also with another institute to comparing that result. And finally, also we published a paper related to all of this process. And it's important, not only this setup can also work with the satellite, we can also, you can see here's only the valve, all of the elements, we can characterize the magnetic field generated with this element. Another thing that I was work in ground segment and operation. Here is the architecture of the mission for the mission operation. We have a ground station that we are using the leaf space ground station network that is around the world. There are a lot of ground stations. So we are using that. You can see also there how the satellite is connecting to this ground station. And we have a mission control station in the university that is in the seaside. So also there is an interlink between the leaf space ground station and the mission control software station university. There's a cloud engine in order to sending and receiving data between us. And the mission control station, there's a mission control software that including the CSP protocol producer in order to preparing data for sending to the satellite. And also there is a front end and back end software. For the back end center, that is the main brain of the mission control station, we develop a lot of software in order to manage the satellite. Post-processing telemetry, mass properties identification is important to knowing the inertia of the satellite after launch. For the health monitoring, to knowing the satellite behavior and if we can detect any failure during the mission. For the orbit prediction, was important to knowing the position of the satellite in the future in order to knowing how many times we can access for the sending telemetry and the command. Also, we prepare the connection between the BETSMA and mission control software, because BETSMA is a comprehensive software to simulate the electrodynamic tether. So for analyzing the mission was important to have a connection between these two. We preparing the uplink command for the calibration of the magnetometer also was very important. We also developed a software for that. A strategy for managing and controlling the hollow cathode was important. Also now we are working also a strategy for collision avoidance of the satellite during the mission. This was, and for the front end, in order to visualize and was much more easily, conveniently monitor the satellite and sending command. Also, we developed in university a software It includes telemetry visualization, health monitoring, tracking, and sending uplink command to the satellite. And already now we are doing in CSAT testing for telecommunication. We have two modules, both of them different frequency. One of them using the S-band, one of them the UHF. So it was very important to testing the telecommunication before launch. And for that, we have three different layers. The CAN only for checking the software. We have a transceiver testing, and also we have the RF signal only with the sending antenna, exactly like that we have in a space, but with less power. And this is my achievement. I have already published 2 papers, and I attend also 3 conferences. I also attended 1 workshop during the last year. And finally, I'm hoping to have a successful mission. Next year, I will come here, I'll present some successful telemetry data and very good information from our satellite, and thank you for your attention.